So thanks for the organizers for inviting me, and thanks Russ for being born 60 years ago, roughly. And I'm sorry that I prepared a slide talk. I feel like I'm a little bit behind the times here with but I can certainly write things on the board if you have questions or whatever. So please feel free to interrupt. What? Well, it used to be that. Well, okay, never mind. Everybody gives slide talks, but okay. All right. This will not advance the thing. So the uniform spanning tree, right? You take a large graph, connected graph. You look at all possible spanning trees. You choose one at random. This is probably everybody knows what that object. And here's an example on the grid, square grid, n by n square grid. There's been a lot of work on this particular probability measure, and it's kind of one of the heroes of modern probability theory is the uniform spanning tree. For many of us, the first place it really occurs in mathematical literature is Kirchhoff with his matrix 3 theorem, and then there's various results in the 30s, 70s, and then Robin P. Mantle discussed it, its relation with the loop race walk, and there are more results which, including, Burton and P. Mantle discussed the determinantal process on the edges, which I will discuss shortly. Wilson gave a nice algorithm for sampling a random spanning tree very quickly using the loop race walk. Then there's a paper, Benjamini, Lyons, Parrish, Frem, who discussed spanning trees on infinite graphs. I'll also talk a tiny bit more about that shortly. And then I did some work on the conformal invariance, and the relation with SLE was, of course, famously done by Lawler, Schramm, Werner in 2003. And now there's a big book, Lyons, Parrish, where you can read all about spanning trees also.
Since you're going way back, there's also Aldous and Broder.
Aldous and Broder, yeah. Well, I didn't have room for anything, but yes. All right. Well, so since nobody has done this yet, let me just explain Kirchhoff theorem, because that's sort of fundamental to the rest of the talk. So if you have a finite graph here, like that one, there's a matrix associated to that graph called the incidence matrix, right, which is where the rows are indexed by edges and columns by vertices, and the entries are 1 and 0, depending on whether the vertex is incident to the edge. Except that in this case, it's a signed incidence matrix where along each edge you put one of the entries as a -1, arbitrarily, if you like. So if you like, you can orient the edges and put the plus sign at the head and the minus sign at the tail. But it doesn't really matter. And then you can define the Laplacian operator as d star d. Sometimes we put this diagonal matrix in the middle, which is the matrix of conductances on the edges. So you can think of C here as a diagonal matrix of conductances. So conductance is just a positive real number on each edge. But you don't have to. You can just keep this to be the identity for most of the talk, for some of the talk. And then the Laplacian is just d star d. And here's the classical equivalent way to write the Laplacian. The Laplacian at f at a vertex is just the sum over the neighbors of that vertex, f of v minus f of w. And when you have these conductances, the conductance multiplies that edge difference. Okay, so then the theorem of Kirchhoff is that, the determinant of Laplacian counts is the sum over spanning trees, and each spanning tree gets a weight, which is the product of the conductances on the edges of that tree. Okay. Probably this is familiar to everybody, right? Anybody? No, I won't ask. Okay, but right. And you have to do it. You can't just take the determinant of Laplacian because it's a singular matrix. It's got the harmonic functions in the kernel. But if you fix so root the graph at one vertex, which means remove a corresponding row and column from the Laplacian, then you can take the determinant, and then that's what I mean by delta sub 0. Okay. That works nicely for finite graphs. For infinite graphs, you have to be a little bit careful. And so maybe our favorite graph is the. Let me just tell you something about Z2. A question about Z2, which maybe is hard to answer right away. But so the Laplacian here is on the top line there, right? Z2 has this nice translation invariance. It's a group, so the Laplacian looks like, in fact, just a convolution operator, except for the minus signs. It's 4 times the value at a vertex minus the sum of the values of its neighbors. If you look at the Fourier transform, the action of the Laplacian on the Fourier transform of the function, then it's just multiplication. Because the Laplacian is just convolution, then when you dualize, it's just multiplication and it's multiplication by a certain polynomial p, which in this case is just this polynomial here. 4 minus z minus 1 over z minus w minus 1 over w. You should think of z as the Fourier transform of the horizontal translation, and w is the Fourier transform of the vertical translation. And so the question is, what is the meaning of this polynomial? This polynomial, of course, has 1, 1 as a root. That corresponds to the fact that constant functions are harmonic. What?
The Fourier transform is respect to 2 variables, but up there the Laplacian is sort of like 1 complex variable.
That's because, yeah, you're right. I just use sort of complex notation here. V plus I, by V plus I, I mean the vertical translation.
You really think right now in.
I'm thinking of 2 real variables. Yeah. So is that okay?
Yeah.
2 real variables. Yeah. And so it's a Fourier transform which has 2. Well, but Z and W are, don't have to be real. Think of them as roots of unity or on the unit circle. Or more generally, we're going to have to think of them as complex numbers, non-zero complex numbers. And if you think of them as non-zero complex numbers, then this thing has other roots besides 1, 1. 1, 1 corresponds to the constant function, the harmonic function on the square grid, which is just a constant function. But the square grid, the Z2, has lots of harmonic functions on it, which are not constant. It's just that the other harmonic functions, grow at some rate, and somehow these other roots of this thing are telling you about, exponentially growing harmonic functions on the square grid. But what, if anything, does that have to do with the spanning tree model? Right? If you're interested in sort of scaling limits or large scale properties of the spanning tree, then when you compute various large scale properties, you have to look at the Green's function on the square grid there's some formula for the Green's function which involves this polynomial in the denominator here, and when x and y are large, when you're interested in the Green's function for faraway points, then the only sort of relevant part of this integral is when is the root on the unit torus. This is an integral over the unit torus, so z and w are of modulus 1, and the only root of the denominator here is at 1, 1. So in some sense, if you're interested in what happens for large x and y, you don't care about any of these roots except for the one near 1, 1. So in some sense, these other roots don't play any role in potential theory in the large. Did anybody understand that? What I mean by that? Okay. Never mind. Okay, let's just go on. That slide was a little bit bizarre, but what if we do something slightly different? Which is take the same graph, Z2, but we'll put some conductances, non-zero conductances on, like the periodic conductances with 2's on every other horizontal column, and all the other conductances are 1, say. So we can't do the same Fourier transform argument because the conductances are no longer periodic. They're periodic with sort of period 2 this time, so that when you do the Fourier transform, you sort of have, well, there's 2 vertices in one fundamental domain, so the natural sort of object is a 2 by 2 matrix rather than you're not just multiplying by a single polynomial. It's not just a convolution because there's two vertices in the fundamental domain. So the action of the Laplacian here on the Fourier space is a 2 by 2 matrix, and it's that 2 by 2 matrix. Well, but you know, what does this entry mean? It means that if I start at this vertex, so the 2 rows and 2 columns correspond to the 2 different vertices here, and the fact that the sum of the weights at this vertex is 5 is that 5 there, and then this vertex is adjacent to the one up here and down there, which are the W and 1 over W and so on. So this matrix is very easy to write down from the combinatorics here. But when you can again ask, right, when is this matrix singular? When is the matrix singular? Well, its determinant is now some much more complicated polynomial in Z and W. There it is. And what is the meaning of the set of zeros of this matrix? Right? In particular, in this case, the set of zeros is a well, if you think of the zeros in C2, it's some Riemann surface of genus 2, right? It's kind of it's got some non-trivial topology, and what if any, is there some way we can understand what this topology is telling us about the Laplacian in this setting? Right, and I can make a more complicated example, and this object will get more complicated, and we would like some probabilistic explanation of this topological fact. Oh yeah, so here's sort of a picture of the projection of this Riemann surface to the plane. If I look at the log of Z and log of W, if I just take C2 and I project it to R2 by taking the log modulus of the coordinates, then you can see that there's this sort of there's these 2 interesting holes there. And so here's the questions, right? What properties of spanning trees on the square grid involve points other than the boring point, the 1, 1 point? All right. Okay, so now let's let me remind you. Let's go back to the definition of the determinantal process on spanning trees. This is a theorem from Burton and Pimentel, 1993, which says that if you have a finite graph, the edge process is determinantal. Maybe I don't need to say what a determinantal process is here. It means that there's some matrix, some kernel, whose minors give you the probabilities of various edge inclusion probabilities in the tree. And here the kernel has a very simple expression in terms of the Laplacian and this function, the incidence matrix D. So you just take D transposed inverse Laplacian times D. And that's the kernel. And even though the Laplacian is not invertible, it's invertible on the image of D transpose. So this is a well-defined matrix. But as we learned from Benjamini, Lyons, Paris, Schramm, on infinite graphs, the situation is not so simple. There's not just one natural measure on spanning trees. There are, in fact, there's the wired spanning tree and the free spanning tree and possibly others. So I'm going to go back and study a very simple infinite graph, right? Before I go back to the plane, right, which is a little bit complicated, let's just start with an even simpler graph, which is a strip, bi-infinite strip. Right, here's a spanning tree on the square grid, a strip on a square grid of width 4. All right, perfectly boring object. I mean, I don't know, boring is not the right word, but perfectly simple object. Okay.
Disconnected, so the boundary condition is not completely free.
It's just part of the. You just see part of it. It's a piece of the bi-infinite tree. Okay. Well, here are some other probability measures on spanning tree-like objects on this grid, on this strip. Right. The first one is just the UST, the uniform spanning tree, which, if you like, you can get it by taking a large, a strip of width n, taking whatever boundary conditions you like, free or wired, and then just taking a limit, and then gets large. But these are other samples of other measures, mu2, mu3, mu4, where the index counts the number of bi-infinite components going from left to right, right? And these are sort of locally uniform, subject to having j components where j is the index.
You can start with mu4.
Yeah, mu4 is kind of easy. And, well,
Are these spanning trees or forests?
they're spanning forests, right? They're essential, what we call essential spanning forests, because each component is infinite.
The forests and trees.
Yes, yes.
Okay.
But, you know, if I look locally, if I look at these pictures, you can't tell that it's a tree or a forest. I mean, if I don't show you the whole graph, you can't tell. So, I mean, locally, you know, each of these configurations is just as...
That one would connect here.
Yeah, but I'm only showing you part of the graph. Right. That's correct. Somehow these are related to each other, and I want to tell you how these guys are related. And here's the theorem, well, the main part of this theorem is these are all actually determinantal, in the same sense that the spanning tree, uniform spanning tree, is determinantal. That is, the probability of any set of edges occurring is the determinant of a matrix, of a minor of a big matrix, of an infinite matrix.
Self-adjoint.
No. Okay, well, don't worry about that comment for now. I'm going to come back to that. But here's the kernel, right? I'll have to explain some of the terms here, but let me just point. So for each j, the kernel is a little bit different. You take two edges, E and E prime, say in one fundamental domain. These are graphs which are periodic in one direction. And so you translate one of them, say E and E prime are in one fundamental domain, and you translate one of them by x, and then there's some integral you have to do to get the entry in the kernel of the matrix. So this is it's a contour integral here. There's a z to the minus x, where x is a translate. So you think of one edge as being here, and the other edge is x. X translates away. X translates away, and then there's some rational function here, which I will tell you about in a second, and then you multiply by z to the x, and you integrate over the unit you integrate over some curve around some closed contour. And the j here is supposed to correspond to the number of components. And you see, and the only place that j occurs on this right-hand side is the contour that you integrate around. So in some sense, these are the kernel here are different Laurent expansions for the same rational functions. Laurent expansions in different annuli. So that's kind of a cool fact. That is, all you have to do is the formula is just the same as the Burton-Pimentel formula. You just have to change the contour of integration, and then you get these other measures. In that sense, they're very natural. Yeah?
So if instead of indexing just by this j, you also had an index that was 4, but it could get bigger too, so it's like j out of k, then
Yeah.
how would that show up?
Everything occurs in this matrix, little k, which I'm going to tell you about now. Okay, what is this little matrix k? This is a finite matrix. In this case, in fact, it's a 4 by 4 matrix, which depends on a parameter z. And what is it? It's the it's the. I have to go to the next slide. Sorry. Let me start.
7 by 7.
What?
Why not 7 by 7?
What about 7 by 7?
How many fundamentals, how many different kinds of edges are there? Just 4.
Yeah, there's. K is 7 by 7. I'm sorry, but the Laplacian is 4 by 4 because so let me explain, right? So before I finish the explanation of the previous, let me sort of warm up to that explanation on this slide. Okay, So we have a graph which is periodic in one direction. And so we can, we're going to define, rather than the Laplacian on the whole graph, we can, do our Fourier decomposition of that Laplacian according to the, the eigenspaces for the translation operator. So I'm going to define Laplacian of z to be the Laplacian acting on the space of so-called z-periodic functions. The z-periodic functions is just the vector space of functions such that, when you shift by 1, when you multiply, they multiply by z. Right? It's like on the Fourier basis, right? You I have this infinite graph. If I want to, I want to look at functions such that the value, if I have some value on this column, then the value on the next column is just multiplied by z, and so on. Z squared a dot 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 z inverse a. Those are called z periodic, right? And that's a finite dimensional space. In fact, it's 4-dimensional in this case because there's only 4 vertices in the fundamental domain, and the Laplacian preserves that space. That's an important fact. Because the Laplacian commutes with translation, it preserves that space. And here's the action of that Laplacian on that subspace. It's just a 4x4 matrix, which involves this extra parameter z. And okay, and once you've got this Laplacian, then Laplacian of z, then you can make this matrix. Well, and I forgot that d also depends on z here, but d transpose Laplacian z inverse d. That gives you, this is like a 7x7 matrix now, k of z. That's a 7x7 matrix of rational functions in z. And they're rational but the denominator involves this Laplacian, the determinant of the Laplacian. So that's what you plug in here.
So, go to the next slide.
Yeah, sure.
What, I see the definition of delta z in the middle.
Yeah.
But what do you mean by saying it's the Laplacian on this space?
Well, the Laplacian on the big graph commutes with the translation operator, and therefore it acts on this space of z-periodic functions. If you take a function in this space and you apply the Laplacian, you get another function on that space.
Right.
And the action of the Laplacian on that space is, because that space is a 4-dimensional space, a linear map from that space to itself.
Canonical basis.
Yeah, the canonical basis, well, this is the basis indexed by the vertices in the fundamental domain. Yeah, see, if I apply the Laplacian to this vertex, I'm going to get 3 times this minus that minus that minus that. So that's 3 minus z minus 1 over z minus b, which is which you see in the first row there. All right, so now what does it mean for this matrix to be singular? Well, you can of course just compute the determinant. It's some big polynomial, Laurent polynomial in z. And it's got some zeros. In fact, it's got 8 zeros. Why 8? What?
You ask why?
I was just pausing.
If you multiply this by z to the 4, you get
Yeah, sure. That's right. Well, the space of harmonic functions on this graph is exactly 8-dimensional. Right? What if I want to describe a harmonic function on this graph? Right? If I pick the values on these 8 vertices arbitrarily, then I can use the sort of harmonic continuation to get the values at these points, because the harmonicity at this point says that this guy is the average of these 4 neighbors, so this one is determined by the other 3. And so I could just, all the other values are determined by these 8 values. So, and of course, the harmonic functions are in the kernel of the Laplacian, and those are exactly so the zeros of this polynomial, in some sense, correspond to the harmonic functions. There's all the harmonic functions sort of grow exponentially, except for 2 of them which don't grow. One of them is a constant function, and one of them is the linear function. Those are harmonic functions which only grow linearly, and the rest of them grow exponentially. And it turns out that the kind of a nice fact, it's not so easy to prove, is that the eigenvalues are all, sorry, not the eigenvalues, the other roots are all distinct and real. And, well, they come in reciprocal pairs. That's not so hard to understand. So let's call these eigenvalues of harmonic continuation. Right, they are eigenvalues of a certain matrix in this case, but for a more general graph, it's not so easy to see that they're eigenvalues of any matrix. But they are always real and positive and distinct, except for the double root at 1. In this case of a planar strip graph. What is harmonic continuation? Yeah, it's the, if you only know partial information about a harmonic function, if I know the values here and I want to know the value over there, I can sort of right. Okay, well, what if we make the strip wider? Here I just computed these roots for a strip of width 32, right, rather than 4. And I plotted them. So I plotted the ones which are larger than 1. They look kind of like that. They fill out a nice curve, right? There's 32 roots larger than 1, and there they are. They're all real numbers, distinct real numbers. But here's kind of a mystery. Suppose that we change the problem back to our case where we had these periodic conductances, right? So here I put 2's on every other vertical column, vertical row. So imagine this is a graph of width 32 this way. And you do the same calculation. You compute the eigenvalues so the roots of this harmonic continuation, the roots of this big polynomial, which correspond to the harmonic functions on this graph. And, okay, something interesting happens. There's this gap in the roots. So the roots fill in this nice interval for a while, and then there's a big gap, and then they fill in another interval. And that gap occurs being right in the middle, 16th root. Okay? Weird. Any physicists? Are there any physicists here? Oh, good.
Before you have these,
Yeah.
and they're inverses and a double root at 1.
Yeah.
So you must not have that anymore. If you have
No, I just plotted the ones which are bigger than 1 because the others are inverses of these.
Okay.
So you see a gap here. There'll also be a tiny gap over here, but it sort of gets washed out.
Okay.
If I took the
middle of the right-hand side.
right, it's in the middle of the right-hand side. Oh yeah. So here's the next. Well, you might as well do one more experiment, which is to put 3 rows, sort of make it periodically, period 3 vertically, still with. Well, maybe I chose something else, like 30 this time, just to make it a multiple of 3. Doesn't really matter. And there you see 2 gaps. One which occurs at 10, and the other occurs at 20, exactly at 1/3 density and 2/3 density. So now, since there's no physicists here, I can talk a little physics without risk of being contradicted immediately. But what distinguishes an insulator from a metal, from a conductor? It's this thing called Bandgap. When you look at an iron crystal or an iron atom, right, it's got a certain amount of electrons, and then they fill up up to a certain energy level, and then there's some. But if you look at some, and then they sort of fill it to the top, and then the top electron is sort of free to float around, and that's what makes them good conductors. But if an insulator, I don't know, carbon or something, there's a gap between the largest filled state and the next state, and so it's hard to. There's an energy gap that electron has to overcome to escape the atom, and therefore, you had to put a really large electric field before that electron will escape and be able to carry charge. And that's my explanation for kind of what's going on here. These gaps, these eigenvalues are like electron energy states, I mean, if I sort of redid everything in terms of the Schrodinger equation also involves the Laplacian and the eigenvalues of the Laplacian. It's a slightly different Laplacian because these are not eigenvalues, but it has a similar structure.
So what is the insulator and what is the conductor?
Oh yeah, the one with the one with this one is a conductor and this one's an insulator. Somehow when you put this slightly inhomogeneous material, it becomes a insulator. Well, it depends on your measure, right? Some of the measures, right? These are sort of the different energy levels, and if you remember we have these measures mu j, where j is the number of components, and if I put in 16 out of 32 components, something interesting happens. If I put in 17 or 16 plus epsilon, 16 times 1 plus epsilon components, then it will start conducting again. But if I put in
These zeros, they always correspond to the number of components.
yeah, for each, I didn't tell us that yet. But you were supposed to infer that. Remember, I realized that I forgot to say that part. I should have said that. Remember, in my original example, there were these roots, lambda 2, lambda 3, and lambda 4. And I said the different kernels of the determinantal process are different Laurent expansions. There were these curves. The kernel was obtained by integrating over some curve of some stuff. And those curves are the curves which are separated by these zeros. Because these are the zeros in the denominator, right? Here's this function p of z. It's got zeros at these points. And therefore, it's got 1 over p of z here has a pole at these points. And therefore, it's, the Laurent expansion in this annulus is different than the Laurent expansion here and there. And those Laurent expansions determine the kernel kj. If you look at this, is like C1, C2, C3, and C4. All right, C4 was the boring one. It sort of surrounds all the zeros, and it's trivial. But all the other ones are sort of interesting. And
Why does it tell you that?
so right. So now suppose that we're in the width large 32 case, right? The zeros line up, and then there's a gap, and then they line up. And if you put in if you put in 16 paths, 16 components going across, right? The system is there's a sort of a large gap before you start getting the 17th one. It's kind of like the mathematicians in an elevator problem. That there's an elevator, and one mathematician gets on, and he sort of stands anywhere, and then at the next floor another mathematician gets on, but they don't know each other, so they sort of immediately move to opposite sides of the elevator, and then at each floor another mathematician gets on, and it starts to fill up. Everybody's feeling a little uncomfortable, so they sort of try to move apart as much as they can. That's what's going on in this model. These paths are trying to repel each other, but suppose in your elevator. Suppose the elevator has a nice linoleum floor with black and white checkers, right? So at some point, the elevator is half full, and there's one mathematician standing on each square, because that's sort of the maximum space. And then what happens when the next mathematician gets on the elevator, right? Everybody feels a little bit uncomfortable, right? It takes a lot of energy for them to sort of move around to redistribute themselves, right? Suddenly the energy is much larger, and that's my that's my explanation for why there's a gap here, right? Somehow these twos, right? The spanning tree likes the two levels, right? But there's sort of enough for one spanning tree for every other group of twos. But when you try to cram in one more component in there, it has to share the twos with the other components, and that's why it costs a lot of energy.
Is this what Russ referred to as elevator music?
I don't remember that. Elevator.
Is there a reason to? Is there any reason to why we should see that the number of roots that you include in the contour corresponds to the number of components?
Yeah, well, that's the theorem. That's non-trivial. Yes, I mean.
Can you take roots that involve some? Can you take contours that involve some other subset roots?
No, that won't give you. If you do something else like that, it won't give you a probability measure, as far as I know. All right, how are we doing? Okay. I'm glad you're enjoying it. Well, okay, so now let's make our strip sort of infinitely wide. So we go back to the whole plane. All right? And now, of course, there's no fixed direction anymore to these paths, right? Once you the plane becomes infinite, you can go in any direction. And so this one variable polynomial sort of becomes a two variable polynomial, which I guess you saw already, this two variable polynomial. And the answer, let me just give you the answer, is that you don't just, you get a whole two parameter family of measures, not just a discrete family of measures. You get a whole two parameter family of, continuous two parameter family of measures, of which the UST is just one of them. So here's sort of the answer for the plane. It's a much larger set, right? The UST is just one of a two parameter family of probability measures on essential spanning forests. And the measures are indexed by the zeros of this P. Well, the P, if you invert both Z and W, you get the same measures. And the uniform spanning tree somehow corresponds to that special point 1, 1 on the spectral curve. This P is the spectral curve for the Laplacian. And the other points correspond to these essential spanning forests where you have these, look locally like these other measures. They have a certain direction of trees all running parallel to themselves, to each other. And there's a certain density and a direction of these other trees. And the two parameters, the density and the direction, determine these 2 points, Z and W, on.
Two-ended trees.
What?
Two-ended trees.
Two-ended trees, yeah. They're bi-infinite. And they have a average slope and a certain density. If you think about how many trees do you cross per unit length horizontally and the number of trees you cross per unit length horizontally, those are two real numbers which describe all these possible measures. And those measures are indexed by points on the spectral curve, or equivalently points in the Newton polygon of the polynomial here. So every point in this Newton polygon of that spectral curve corresponds to one of these measures.
So this map from ZW to the slope is not 1-to-1.
It's 2-to-1. The map from ZW to the slope is 2-to-1, except over the integer points. So there's a larger story in the background, which I'm going to skip over for lack of time. I apologize. But it's not the first time we see these measures occurring in nature, or in mathematics, I should say. This picture sort of inspired the whole my discussion here. This is a picture from 2004. There's something called the cube recurrence, which is a recurrence for a real valued function on Z3, which was discovered by Gabe Carroll and David Spire, and they made these in some combinatorics, some interesting discrete integral system in combinatorics, and they discovered these nice objects called cube groves, which are, well, here's a sample of one of those cube groves chosen uniformly at random, and it is a certain essential spanning forest with components which with particular boundary connections. So the point here has to be connected there. The point up here has to be connected over there by the same component. And up to those very simple rules, you take a uniform random sample and you get something like this picture. And the part of the result, which was part of the goal of the talk, is to sort of explain this picture, or explain what happens when you zoom in to a point in this picture. You're going to see one of these measures. the spanning tree measure on the whole plane, the spanning forest measure on the whole plane, which is determinantal. Okay. Combinatorics, skipping that. Okay, yeah, so there's the theorem. The measures, mu, now the measures are indexed by 2 points s comma t. These are the 2 points in the Newton polygon, or if you like, I can also parameterize them by the points z and w, which are the zeros of the polynomial here. And then again, the theorem is the same. The kernel of the determinantal process is the same, is just given by the usual formula for the kernel from Burton and Pimentel, except you change the contour of integration by, instead of integrating over the unit circle, you integrate over some other circle, right? So z, you integrate over the circle of modulus e to the x and e to the y for w. But in this case, somehow when we're on the plane, we can vary these parameters continuously rather than discretely.
What are capital X and Y?
They're just oh yeah, well, they're related to S and T. They're the Legendre duals of S and T. How do I say that? Right, so X and Y are functions of S and T. Yeah. Here's the picture. Where's the picture? Here's the picture. Remember this picture of P, right? This is a picture of log of the zero set of P in the log Z, log W plane, and X is a modulus of Z, and Y is a modulus of W. And if you pick the modulus of X and modulus of Z, you'll see that will determine Z and W up to a complex conjugation. But then there's this homomorphism from this picture, diffeomorphism from the interior of that picture to the Newton polygon, which is the gradient of the gradient of the free energy, if you like. So you can either use your S and T coordinates, which are somehow simpler, or you can use these ZW coordinates, or you can use the X and Y coordinates, which are just the modulus of Z and W. It's a bit of a long story, so I went too fast, but you don't really need to know that. Let me just show you a couple of pictures. Here's the, for these measures, mu st, you can ask what's their free energy, right? The log of the partition function, normalized partition function, and as S and T vary over the diamond region, it's a nice convex function. And you can see something interesting. I think you can see something interesting, right? There's a little point here where there's a non-differentiability point. There's one there, there's one there. Those are the insulators. Wait a minute. Yeah, those are the insulators. So it's sort of everywhere it's a conductor, except at that point it's an insulator. Never mind. They correspond to the holes in the thing here. The holes in the Riemann surface map under this map over here to single points over here.
How are the three special then?
How is what?
How are the three special?
How are those?
How are the spanning tree special at the insulator point?
Yeah, they have the spanning tree process, spanning forest process has an exponential decay of correlations rather than a polynomial decay of correlations. Oh, I have a picture. Where is that picture? Here's a picture of the. No, this is not one of the pictures. Never mind. It's a picture of the. This is a conductor picture, but. Okay, I'm out of time, so I'm flitting around randomly here. But you can also do the same thing with the massive Laplacian, which counts sort of rooted spanning forests. So take a rooting spanning forest of a strip, but condition it on having a certain number of bi-infinite crossings. Everything goes through, and we're so used to sort of ignoring this case of the massive Laplacian because it's doesn't have a nice scaling limit. It's not conformally invariant.
By massive Laplacian?
You take the Laplacian plus a positive constant. You take the determinant of this matrix. M is a positive constant. That counts rooted spanning forests with weight m per root. So it's a spanning force where every component has a root, and the weight is m per component. And it's something that people have known about since almost the time of Kirchhoff, but physicists don't really care about it because it doesn't have any scale invariance. It's not conformally invariant. But the interesting thing about this model is that when you start looking at these other measures where you have many components, you recover you see that only you recover the conformal invariance. Only the case where ST is 0 where there's no infinite components is it actually not conformally invariant. The fluctuations in this picture, right? Here's a picture where it's a massive spanning tree process. So each component here has a weight m, but I've conditioned on having a certain density of horizontal components. And in this case, the fluctuations are again conformally invariant, and they're probably given by a Gaussian free field again, the fluctuations, but I don't know how to prove that. So that's the end. Thank you.